So in our previous lessons, we talked about radioactive decay, alpha decay, beta decay, and gamma decay. Now let's use that knowledge to handle this question. We said in those decays, a parent will always produce a daughter and some rays will be given. So let us see here. Question 2a says, find the values of P and Q from the equation below. 3 marks. So the values of P and Q, where P is here, Q is here. And remember, this is the parent. Q represents atomic number and P represents the mass number. So that's what the examiner is interested. Now, for us to get this mass number, we should know all the mass numbers. And even for us to get this atomic number, we should also know all the atomic numbers. So the parent has atomic number what? Q, unknown, and P, unknown. But the daughter, the two are known. Mass number is known, 230. Atomic number is also known, 90. Then when you come here, there is a ray which is produced. This is a symbol for alpha particle. There are two alpha particles. An alpha particle is a helium atom. How do you write it? You write it like this. Helium atom, atomic number 2, mass number 4. But there are two of them. So we have to write two of them. So for us to balance, as part of our solution, we shall write X the way it is with the unknowns. We shall also write Y the way it is. This one is already known, although we don't know the name of Y, but we know it is a daughter. Then we write two alpha particles. One alpha particle is written like this. So if there are two, you add another one. You see, to make a total of 2 alpha particles. Then from there, you now balance. How do you balance? The unknown is what? P. The only unknown on this side, as far as the mass number is concerned, is P. You know, you are supposed to balance. You add all the mass numbers on this side of the arrow must be equal to all the mass numbers on this side. You do that for mass number and atomic number. Let's start with the mass number. Now with the mass number, we have here P on this side. Then this side we add 230 plus 4 plus 4, which means P is equal to 230 plus 4 plus 4. So that's what we write here. P equals to 230 plus 4 plus 4. And when you add, you get 238. Then we come down for atomic number. Q is the only unknown this side, and is the only atomic number. So we add all the atomic numbers this way must be equal to all the atomic numbers this way. But now here we only have Q. So our Q is going to be equal to 90 plus 2 plus 2. And that's what we write here. Q equals to 90 plus 2 plus 2. And when you add this, you get 94. How many marks were we supposed to get here? The examiner says we are supposed to get 3 marks. Now, how do you get all the marks? The first mark goes to the equation, which you tried to write, you know. Then the calculation now. 1 mark for the working and the answer for P. 1 mark for the answer and the working, the whole working. Okay? So you get your 3 marks. B, state the composition of the parent nuclide X. So when you look at this equation, which one is X? This is X. This one is Y. This one is an alpha particle. There are 2 of them. So when you are writing 2 alpha particles, you can separate them the way we did here. You write 1 by 1. Or you simply write 1 of them. Then you put a 2 in front. You see? These are 2 alpha particles. Now we are supposed to what? In this, the whole of this equation, we are supposed to state only one thing, the composition of the parent X. And where is the X? X is this one. This is the parent. Composition means, now we are going to look at X as an atom. And we know inside an atom you have electrons, you have protons and neutrons. So the examiner wants the number of those things. And mainly wants the protons and neutrons. But you can state the electrons as well. Now we know the number of protons is the same as atomic number. And this is the atomic number. So the number of protons is already 94. And in an atom, the number of protons is the same as the number of electrons. So if the protons are 94, then the electrons are also 94. Then the neutrons, how do you get them? You subtract this minus this. And when you subtract these two, if you use your calculator very well, you get 144. So there are 144 neutrons. Meanwhile, the protons are how many? 94. And the electrons are also 94. So we simply tell the examiner that this atom you are talking about, X, has how many protons? 94. What about electrons? They are also 94. And the neutrons, after subtracting, they are 144 neutrons. And you get all your marks. Then we go to question 3. Complete the equation below. This is the equation. The parent is W, atomic number is given, mass number is given. The daughter is X, atomic number given, mass number given, plus one of the rays, which is now not known. And we are supposed to, this atomic number is Y, mass number is X. And the equation is complete the equation. So we first need to understand what is the value of X and Y. Then we can complete the equation. As usual, let us look at the mass numbers. Here we have only 131. Here we have 131 and X. So when you add this, it is X plus 131 gives you 131. And that's what you write here. X plus 131 gives you 131. Now you want to remain here with X on this side of the equal sign. So you want to remove 131. So here 131 is positive. When it crosses this side, it becomes negative. So X will remain alone and equal sign. When this 131 crosses this side, it becomes a minus. So it is 131 minus 131. You get 0. So X is 0. Then we do that for Y also. Y plus 54 equals to 53. And that's what we write here. So we want to remain with the Y only this side. So what do we do to plus 54? We take it this side. It becomes minus. So our Y is going to be equal to 53 minus 54. We know 53 is big, is what? Is less rather. Is less than 54. So a smaller number minus a big number, the answer is negative. So here is negative 1. So after knowing the values of X and Y, we can now write the equation. You write it exactly how it was, but you replace X with 0 because our X is 0 and Y is negative 1. So our equation is going to look like this. Then in part B, the examiner wants you to name B. What is this element here? What is this? Is it a ray? And what is it? So what is that? What is that thing which has mass number 0 but atomic number is negative 1? First of all, having a negative means this thing is negatively charged. This should be a beta particle because a beta particle is an electron. It has mass number 0, atomic number 1, but negative because it is negatively charged. We all know electrons are negatively charged. So this is a beta particle. So you now answer the examiner and say B is actually this element here, this thing here. It may not even be an element, is a beta particle. Now let's move on to another interesting term, activity of a radioactive sample. What do you mean by activity of a radioactive sample? You know, a radioactive sample, anything which is radioactive, it keeps on what? Decaying. And when it decays, it reduces in size. So how many atoms are decaying compared to the time? So activity here means the number of atoms which decays per unit time. So mathematically we would say if you have 20 atoms decaying in maybe 5 seconds, activity would be 20 atoms divided by 5 seconds. The number of atoms per means divide the number of atoms which decays per unit time. Now we want you to note the following, that activity is different. Every radioactive element has its own activity. So activity differs for different radioactive elements. You see, some are as small as seconds, others are in millions of years. So from 1 second to millions of what? Years. So what does that mean? There are those radioactive elements whose activities are in what? Months, years, minutes, weeks, and so on. So starting from seconds to millions of what? Years. Now, how do you measure an activity of a radioactive element? You use what we call radioactive detectors, and you do that in the laboratory. So activity is measured in the laboratory using radioactive detectors. You see, examples of radioactive detectors are cloud chambers, GLE means the gold leaf electroscope, and a Geiger-Müller tube, GMT. Now, a gold leaf electroscope, a Geiger-Müller tube, cloud chambers, these are examples of radioactive detectors. We use them in the laboratory to measure activity for every radioactive element so that we are able to compare them. And that is why we came to a conclusion that after doing the experiment, every radioactive element has its own what? Activity, ranging from 1 second to millions of years. So let us look at a graph of count rate against time by a GMT. We have just said that GMT means Geiger-Müller tube. It is one of the radioactive detectors which we use to help us in the laboratory to measure activity of every radioactive element. So we know a radioactive element keeps on decaying, and decaying means it keeps on reducing. You know, the number keeps on what? Reducing. The activity keeps on what? Reducing. So this graph shows how a count rate or activity of a radioactive substance, what happens to the activity. So on the y-axis we have what we call the count rate, that is on the vertical axis. Then on the horizontal axis we have time. So when you plot a graph against a count rate, okay, graph of count rate against time, you end up with this kind of curve. And this type of curve has a name, we call it a decay curve. Now you'll realize that this curve does not touch the horizontal, does not touch this axis, the time axis. There is a way it moves. Look at my hand. Now it is realized that the reason why it does not touch this, because of what we call background what? Radiations. We are going to talk about background radiations shortly. So this curve, this kind of graph is called a what? A decay curve. So when you are studying activity of a radioactive substance, you want to know how a radioactive substance what decays, and then you monitor the count rate according to the rate meter, the machine you are using for measuring. So it will give you the count rate against time. In 2 minutes, what is the count rate? In 3 minutes, what is the count rate? Then you plot the what? The graph. So you end up with such what? A curve. And this curve, this kind of graph is called what? A decay curve. Now we have just mentioned background radiations, and I've said the reason why this curve does not touch the horizontal is because of what? Background radiations. You see these arrows from here up to here, it is caused by background radiations. So what are background radiations? Background radiation simply means, they mean nuclear radiations which we are exposed to. You know, when we talk about nuclear radiations, alpha particles, beta particles, gamma rays, you know, the radioactive substances keep on decaying and producing these rays. Those nuclear radiations, so background radiations, these are nuclear radiations we are exposed to. Now, where do these rays come from? What are the sources? So you mentioned them. From the cosmic rays, that is from the sun. So cosmic rays from the sun produce nuclear radiations. Is there anybody who does not receive any heat from the sun? No one. We are all exposed to the sun. So those rays, cosmic rays from the sun, they contain nuclear radiation. So we are exposed to. Now those rays, radiations, we call them background radiations. Another source of background radiation is our own bodies. Do you know that our own bodies, we have radioactive substances? Yes. there are some radioactive substances inside our own bodies, and they produce radiations. So we are exposed to that. Another source is the air. Is there anybody who is not feeling air around you? First of all, you breathe in air. So air also is another source. Then we have the rocks. You know, some rocks have radioactive substances. So these are the sources of background radiations. So we define background radiations as nuclear radiations we are exposed to naturally, coming from cosmic rays from the sun, our own bodies, air, and even the rocks. Okay? So, because of these background radiations, the graph is not, they cannot allow the graph to touch here because they are always there, present. Now, let's look at another interesting thing, cloud chamber tracks. Before we understand what we mean by cloud chamber tracks, I want to remind you that we have just talked about a cloud chamber. We said a cloud chamber is one of those radioactive detectors. We use them to detect radiation. If we want to know whether alpha particles are here, beta particles are there, or gamma rays, you simply bring these things. So, cloud chambers are examples of radioactive detectors. So what do we mean by tracks? Now, these tracks are, I could relate them to pictures, but to be more precise, there is an experiment which can be carried out with a cloud chamber. So what you do, you pass the alpha particles in a cloud chamber, beta particles, and gamma rays. Then you see there is some bright light which is produced. And the way these lights are produced, the reflections which are produced, they don't look alike. I want you to look at this diagram. There is one where you see straight, you know, they are straight but thick lines. You see, straight and thick lines like this. Then there are those which are straight but they are thin. You see? Then there are those you will see they are twisted. They are short and twisted. Now once you see the short and twisted, those are gamma rays. Once you see the ones which are straight but thin, those ones are for beta particles. And once you see the ones which are straight and thick, these ones are for alpha particles. So the cloud chamber, now those pictures or those reflections or those lines, we call them tracks. And that's why we call this cloud chamber tracks. So this is a cloud chamber track for alpha particles. You can see straight and thick. Straight and thick tracks. We call them tracks. Then for beta particles, they are straight but thin tracks. Then for gamma rays, they are short and twisted. So we can summarize here and say, in form of NB, that alpha particles produce straight, thick tracks. What about beta particles? Beta particles produce thin, straight tracks. What about gamma rays? Gamma rays produce short, twisted, and thinner tracks. So these ones we call them cloud chamber tracks.